Unleashing the Power of the Future, a journey into nuclear fusion. Have you ever wondered whether there's a factor behind the massive changes in the energy production environment that might be fundamentally altering how we develop power? Imagine a future where energy is pure and limitless, unencumbered by concerns about the environment and depleting resources. Imagine that this isn't simply the stuff of science fiction novels. Instead, picture it as the exciting frontier of nuclear fusion, where atoms fusing open the door to an endless supply of energy. Can we reimagine our energy future by harnessing the power of the stars? Come along on an enthralling trip with us as we unravel the mysteries of nuclear fusion and explore its potential to create a bright, sustainable future. Are you prepared to venture into the unexplored regions of pure, boundless energy, the fundamentals of nuclear fusion? Let's begin with the fundamentals to fully understand the wonders of nuclear fusion. Nuclear fusion is the process of joining light atomic nuclei to create a heavier nucleus, in contrast to nuclear fission, which is the process that fuels our modern nuclear reactors. The most likely option to do this on Earth is the fusion of tritium and deuterium hydrogen isotopes. Energy production from nuclear fusion has the potential to reach previously unheard of levels. According to the well-known equation, ERMC2, the process entails transforming a small portion of the mass of the interacting nuclei into energy. Fusion is an intriguing option for supplying the world's expanding energy needs because of its efficiency, which is orders of magnitude greater than that of any other energy source. The sun's blueprint. For billions of years, nature has been honing the craft of nuclear fusion, and the ultimate fusion reactor is none other than our sun. Massive quantities of energy are released during the fusion of hydrogen atoms at the sun's core, when temperatures reach millions of degrees. Scientists want to recreate this dance of the stars on Earth in controlled surroundings. Scientists can learn more about the prerequisites for maintaining regulated nuclear fusion events by examining the sun's fusion process. The challenge that has spurred decades of study and invention is to replicate the sun's efficiency in turning mass into energy while retaining stability and control. The fusion reaction, tritium, which has 1 proton and 2 neutrons, fuses with the nucleus of deuterium, a kind of hydrogen that has 1 proton and 1 neutron. Incredibly high energy, helium, and a neutron are produced by this fusion event. Furthermore, there is a practically infinite supply of the reaction's fuel, deuterium and tritium, which are plentiful and can be produced from water and lithium. To fully use the strength of this fusion process, positively charged atomic nuclei must overcome the strong obstacles posed by the Coulomb force. Achieving temperatures and pressures so high that the nuclei can overcome this resistance and combine to release energy is crucial. The goal of cutting-edge technologies like laser compression and magnetic confinement is to controllably produce these extreme environments. Challenges and breakthroughs. Although the advantages of nuclear fusion seem fascinating, there are obstacles in the way of achieving this goal. The main challenge is producing and maintaining the extremely high temperatures, hotter than the sun's core, necessary for fusion. Let us introduce you to tokamaks, stellarators, and laser inertial confinement, which are state-of-the-art devices that aim to control the extreme pressures involved in the fusion process. Massive devices known as tokamaks like ITER contain and regulate superheated plasma, which reaches temperatures of hundreds of millions of degrees using magnetic fields. An alternate method that aims to create more stable and continuous fusion processes is provided by stellarators, which have complex magnetic structures. Significant progress has been made in the search for sustainable fusion energy with both configurations, tokamaks and stellarators. Tokamaks, such as the well-known ITER, International Thermonuclear Experimental Reactor, contain the superheated plasma by use of strong magnetic fields that keep it from making contact with the walls of the reactor. Stellarators provide an alternate method due to their distorted magnetic fields. By combining decades of study and teamwork, these concepts bring us one step closer to realizing sustained fusion reactions. The greatest brains from several nations come together to build and run these enormous machines through multinational cooperation. For example, ITER brings together experts from 35 countries who share their knowledge to solve the technical and scientific obstacles in the way of controlled nuclear fusion. Laser inertial confinement. Accuracy is essential when working with laser inertial confinement. The fusion reaction is started when laser beams focus on a small pellet of fusion fuel and compress it to extremely high densities and temperatures for a brief period. Even though this approach has many advantages, research is still being done to find a solution for the numerous technological difficulties. An alternative to magnetic confinement is offered by laser inertial confinement, which depends on the exact synchronization of several powerful lasers. It will take advances in laser technology and materials science that push the frontiers of what is now achievable to achieve the required compression and preserve stability. Worldwide collaborations. Scientists, engineers, and researchers from all over the world are combining their knowledge and resources in the genuinely worldwide pursuit of nuclear fusion. Initiatives such as the 35-nation ITER partnership serve as prime examples of the common goal of utilizing nuclear fusion to advance humankind. International cooperation includes exchange of resources, expertise, and even building of facilities like as ITER. It goes beyond research and development. In addition to accelerating development, this international collaboration promotes unanimity in the face of the world's energy concerns. Environmental impact. The small environmental impact of nuclear fusion is one of its most appealing features. Fusion reactions don't result in persistent radioactive waste, in contrast to conventional nuclear fission. Fusion is a strong contender for a clean, sustainable energy future since it emits no greenhouse gases, supporting international efforts to tackle climate change. The world is facing an urgent need to switch to greener energy sources, and nuclear fusion appears to be a game changer. With its nearly limitless supply of fusion fuel and its environmental advantages, nuclear fusion is positioned as a key component of the renewable energy solutions grid. Environmental impact. One of the most alluring aspects of nuclear fusion is its minimal environmental footprint. Unlike traditional nuclear fission, fusion reactions produce no long-lived radioactive waste. The absence of greenhouse gas emissions makes fusion a compelling candidate for a clean and sustainable energy future, aligning with global efforts to combat climate change. As the world grapples with the urgent need to transition to cleaner energy sources, nuclear fusion emerges as a potential game changer. The environmental benefits, coupled with an almost infinite supply of fusion fuel, position nuclear fusion as a cornerstone in the mosaic of renewable energy solutions. Conclusion. Is the fusion of atoms the revolutionary force our planet sorely needs to tackle environmental and energy-related problems? Imagine a time when the stars in our labs open the door to cleaner, greener solutions, and plentiful clean energy is a real thing rather than just a pipe dream. Are you prepared to be a part of a revolution that may change the way the world is powered? If you want to be informed about the most recent developments in nuclear fusion technology, like, comment, and subscribe. Your participation keeps things moving forward, and we are grateful that you are joining us on this exciting adventure to discover the seemingly endless possibilities of using the sun's power locally on Earth.